Okay. I'm Thomas. I'm a fifth-year PhD student with Dusty Schroeder at Stanford.
I'm Ben, postdoc at Mines, working with Matt.
I'm Danny, a third-year PhD student working with Alex Roble at Georgia Tech, and we're convening this morning's session.
And then, I guess without anything else, Kirsty Tinto is going to start us off with an invited talk about rings. I don't know if you want that.
I will, thank you. I'll give this a go. And maybe that. Okay, thanks. So yes, I'm Kirsty Tinto, and this is a report on a SCAR, the Scientific Committee on Antarctic Research Action Group called RINGS. And it's an international group who are focused on looking at the Antarctic coast and trying to provide boundary condition constraints to improve our mass balance estimates for Antarctica. I'm speaking for the action group. The steering committee are named on this slide. The action group is large and growing. There's more than 80 members. People sign up as individuals, and then they can send in their institutional logos, and Kenny Matsuoka can try and fit them on this page, which is becoming increasingly difficult, which is the thing that brings us all great delight, because it's good to have people involved in this effort. So what's RINGS? What are we doing? The problem that we want to solve is the problem that everybody in this room wants to solve, that the projections and understanding of Antarctic contributions to sea level is really uncertain. And the solution to that we see is to engage the international community to do coastal surveys to constrain the boundaries of Antarctica. So the action group was established in the spring of 2021. It organized its first international workshop in Norway in 2022. That was a hybrid affair, so there were a lot of people who were there in person. The goals of the workshop were to identify the key science questions that this group would try to address, to work out what the priority measurements would be to address those questions, and also what came from the workshop was developing group values and expectations that will help these diverse groups to work together in a constructive way, because there's a lot of us. There was a second meeting in the afternoon of one of the sessions at the Instant meeting that was in Italy a couple of weeks ago, and there is a gigantic manuscript that's in preparation that will bring together the results of that workshop and a lot of the analyses, some of which I'll show here, that are coming from the group to try and define what these surveys should be. So the problem again, this is the contribution for Antarctica to projected sea level rise out to 2100. This is the contribution of Antarctica to the uncertainty in that measurement, and that's what we want to beat down, the uncertainty of what we're doing. There's a large number of processes involved, and there's really inadequate knowledge of just the boundary conditions of the coast of Antarctica. And there's inconsistent knowledge as we go around the continent. And so this is why we need kind of a cohesive survey strategy to go all around the continent. This figure is just to reinforce the idea that it's a complicated system. So I don't think I need to spend too much time on that for this particular group. There are many components that go into this mass balance question, and many of them are limited by the observations that we have. An example of that is, oh, I didn't turn my clock on, is just in the bed topography around the grounding line. So this is from the BedMap 3 database that came out recently. This is within 100 kilometers of the coast, and in short, red areas on these pie charts are the ones where you're not within 5 kilometers, dark red, you're not within 5 kilometers of a data point. So we don't know the grounding line area well enough in bed topography around Antarctica. It's not the only thing we don't know well enough. There's a lot of uncertainty in surface mass balance, and these are ensembles of surface mass balance models, and you see the rainbow color does a circuit around the coastline. If you track that rainbow around the coast, this is the dark blue is the mean estimate of surface mass balance, and the light blue is the standard deviation. And they kind of follow each other around a little more closely than you would like. So we need to understand the bed topography better. We also need to understand the surface mass balance better if we want to understand the flux of what's moving across the grounding line. Another area, once we've moved across the grounding line, and to understand how heat gets into the ice sheet, we need to understand the topography in the sub-ice shelf cavities and all the way out to the continental shelf. There's been a lot of work done in that, but even in the areas where we have done quite intensive surveying with aerogravity, we're still, there's like 30% coverage of patches of the Earth that we actually know how deep it is to run these models. So that was the big question, and it is the international community, and SCAR is brilliant for that. It's a place where you can have grassroots groups come up and come together to figure out how to address problems in the same way. And so that's what the action group is trying to do. Action groups are quite short-term things that have targeted goals. And what this action group has been doing so far is to define the area that we are interested in, to design the sorts of measurements that we need and give ideal survey recommendations to the community at large, and then to try and coordinate between the surveys that come up and that different nations are expecting to undertake, so that we can make a cohesive product that can be used by the modelling community that's involved in this and can ultimately answer the questions we need to answer. So the survey strategy is focused in 3 areas. There's a landward ring, which is talking about grounded ice, it's talking about basal properties, subglacial hydrology, those sorts of things. A primary ring, which is really around the grounding line, and looking for that as a flux gate and looking at the processes that control mass flux across the grounding line. And then a seaward ring, which is quite a broad ring in various places, that's trying to constrain how ocean heat moves in to the grounding line. There's a suite of recommended instruments here, and obviously there need to be process studies in some places, and then a comprehensive survey that we can use to apply what we've learned from those processes around the continent. Other things ways that the action group is trying to support these cohesive surveys. This is a projection from ISMIP 6 models of working out where the grounding line is going to be by 2100, so that we'll at least have surveyed in that far if we're going to make these useful projections. So we've identified an area of interest that everybody can be targeting their surveys at. We've also gone into detail of what sort of survey planning would be ideal. This is an idealized grounding line product that takes into account where we need data, how close to the grounding line inboard, always on grounded ice, and what's actually practical for an airplane to fly, because a lot of this is going to be done by aerogeophysics. By putting on a line like this, different surveys can work, and if there are 2 surveys that are working adjacent to each other, they'll be able to overlap the same segment. They'll be able to target this cohesive product of a line. So we're giving survey recommendations for people to work out what little piece of it they can do and how that builds into their bigger picture. There have been a number of surveys that have been proposed. We saw some of them shared a couple of weeks ago. This was one of the first ones that Kenny was sort of offering up as an example of how a rings survey could go. And it's a lot of the different nations who are involved around Dronningmogland and Enderbyland who send science capacity to the areas of their national interest and fly some targets each year. And by talking about what do we actually want to do together, there is a collaboration that's growing to try and get a rings type survey put together. They're hoping to do the first flying in this coming season, and then there's going to be more coming on. There were other projects from other nations that were being presented, and we're hopeful that a lot of those are going to be funded. And this really does represent a possibility for people to find out who in the international community is making measurements in the place that you are interested in, and can you get involved with that? Can you get access to the data? Can you contribute an instrument or a student? It's all about finding out who's doing what and trying to do it together. So the SCAR Action Group, future looking. Action groups, as I said, are short-term things. So this one's been renewed. They're renewed in 4-year chunks, and this one's been extended out to 2026. The initial goals were to scope the problem, to talk about where do we need new information, that's a problem. And so the new goals are to support the surveys that are going to come in. It's to endorse projects, it's to show on a map where each of the proposed surveys might be so that you can see what's happening and coordinate together, and then to make sure that as a community we do have exchangeable data and a way to make all these surveys work together. Next meeting's in Chile in August next year, and if you want to get involved in SCAR, there is a US SCAR, and Lynn has a poster out there that you should look at because you could join both of these groups.
Thank you. You can leave it there. Cool. And Marion McKenzie is going to take us back in time through some rocks next, I think. Great. Thanks. Take it away.
All right. Hi, everyone. My name is Marion. I am currently a postdoc at Colorado School of Mines, but today I'll be presenting some of my work from my final chapter of my PhD at the University of Virginia. And I will explain in a moment why I'm presenting things from Washington State when this is the West Antarctic Ice Sheet Conference. So we already know that parts of the Antarctic ice sheet contribute material to the global sea level at different rates across the ice sheet. And one of the things that modulates that contribution of ice to global sea level rise is solid earth dynamics, which we heard about from Terry yesterday. And so the rheology of the Antarctic Peninsula is very similar to that of the Puget Lowland, which is a low-lying area of Washington State that was glaciated by the Cordilleran ice sheet during the last glacial maximum. And this area has very high rates of uplift. And so to test whether or not this glacial isostatic adjustment or solid earth movement could be a potential for stabilizing marine terminating glaciers, this is a really good place to look to see if it could be an analog for future loss of Antarctic Peninsula outlet glaciers. And just so we're all on the same page, the phenomena of glacial isostatic adjustment is when you have loading of ice sheet on the crust, which causes crustal deformation, which then also leads to the flow of the asthenosphere out of the way on the scale of millimeters per year. And then during deglaciation, you get rapid crustal uplift from loss of ice sheet mass, and then the asthenosphere flowing back into place again over those long timescales. And so GIA has been theorized to stabilize marine terminating ice sheets, but this hasn't been tested empirically until now, which is why I turned to the deglacial record of the Northern Hemisphere. And so the Puget Lowland, like I mentioned, previously glaciated by the southernmost Cordilleran ice sheet during the last glacial maximum, is a good place to test this. And so I'm looking at sediment records, and I'm curious to see how they record glacial ice and landscape evolution and how this is an analog. And I'm also looking at the timing of landscape evolution in comparison to ice advance and retreat across the Puget Lowland of Washington State. And so this is Whidbey Island. This is about 2 hours west of Seattle. This region has a lot of glacial record in outcrops across the entire island. And so ice sheet and landscape evolution co-evolved across Whidbey Island, but there are also proposed rapid landscape changes due to the rheology of this region. And prior ages suggest that final ice presence in this landscape was about 15,000 years ago. I'm going to start at the central site of Penn Cove and dive into the stratigraphy of what we see and what it's telling us about the co-evolution of landscape and ice interactions. And so this is what a conglomerate stratigraphic column that I developed looks like. And we can separate the facies into interglacial, which are present before the last glacial advance into the region, and then our glacial till, followed by the proximal facies as the ice is retreating. And when we look at the grain size distributions, these self-organize into the two groups of interglacial and glacial facies. But for the purpose of this talk, I'm just gonna focus on the glacial and post-glacial material that we find in this outcrop. So I also use radiocarbon dating to get a sense of how long ice was in this location. And so in this stratigraphic column, most of this is glacial till, but there are presence of articulated marine shells, which is an indication that ice was proximal in this location, but there was a marine presence allowing for these shells to be deposited under the ice sheet. And so when we date the shells that are present in this location, they come to about 12,100 and 12,900 years ago. So already off the bat, we're seeing that ice is present in this location for 3,000 years longer than was previously established in the literature. But we also see that ice was proximal to this location for about 1,000 years, indicating that there was stability of this ice sheet while it was in this marine terminating environment. If we go to the southernmost site on Whidbey Island, Double Bluff, there are also the presence of these articulated shells, indicating that the ice was retreating into a marine environment. However, when we go a bit further north to West Beach, which is further north than the Penn Cove site where ice was found to have been stable for about 1,000 years, there is evidence of ice retreat into a subaerial environment. And this is present in the grain size distribution of the outwash that we see, as well as the lack of shells that are in these materials. After the ice has completely left the region, we see a resubmergence of the landscape into a marine environment by about 1,500 years ago. And again, at the most northern site, we see evidence of the ice retreating into a subaerial environment. And just to kind of put it all together, this graph is showing the glacial and post-glacial material that I've mapped across Whidbey Island. So on the left side of the screen is Double Bluff, the southernmost site. On the right side of the screen, Cliffside, which is the northernmost site. There is direct glacial deposits at almost all of these sites. But at our southernmost sites, as the ice is retreating, we see evidence of retreat into that marine environment at about 12,000 years ago and stability for 1,000 years at Penn Cove. This is also supported by grounding zone wedges that we see across the area. So not only do we see this in the stratigraphic record, but also in the geomorphological record, there is evidence that there was sedimentation to the ice front, and those have been mapped in the past as well. And then northward of that Penn Cove site of stability, we see subaerial retreat of the ice into that now above sea level landscape. And then after the ice is no longer in this location, we see a resubmergence, which also suggests that this landscape can move between a marine and a subaerial environment very quickly, and that there is evidence that this rheology leads to rapid landscape shifts as well. And so I've hit this point pretty hard, but again, with this work, we find that the ice was in this location for 3,000 years longer than previously thought, with at least 1,000 years of ice standstill. But this has significant implications for meltwater pulse 1A contributions of the Cordilleran ice sheet. We also see in the stratigraphy across Whidbey Island that there's a lot of spatial and temporal variability in retreat styles, and this provides evidence that solid earth is a viable option for creating stability in a marine terminating ice sheet. And this empirical evidence is applicable to the Antarctic Peninsula due to the very similar rheologies, which is the crustal thickness as well as the mantle viscosity between these two locations. The University of Virginia is in the traditional territory of the Monacan peoples. These research sites are located on land historically and currently inhabited by the Stillaguamish, Tulalip, Swinomish, Cayuse, Umatilla, and Walla Walla peoples, custodians of the land time immemorial. As ancient peoples who thrive today, I acknowledge and respect their stewardship of the land past, present, and future. I would like to acknowledge my funding sources as well as my research and data support, so thank you.
Cool. Thank you, Marion, and also thank you for being perfectly on time. And we have Rob Larter next, taking us back south. Thank you.
Okay, thanks to the WAIS Committee for giving me the opportunity to talk here and present some data that we collected on a Palmer cruise about 3 years ago. My co-authors here are the PIs of the Thwaites Offshore Research Project and the students who participated in the research cruise on the Palmer. So, various studies in the Amundsen Sea have identified a boundary running across between the inner shelf, where there is crystalline basement in many places at or near and that here. So when you go further offshore, there's the sediments. There's a dipping stratigraphy with an increase in overall thickness of the strata going offshore. And that's shown by this figure, which is a schematic drawing a lot based on regional seismic lines along that red line on the map. However, we already know that the inner shelf is not totally barren of sediments. So Alex Vitas and colleagues showed that from a transect of sediment cores, and what you're looking at here is just the top half meter or meter of those sediment cores, that there's a pervasive drape of fine-grained sediment of sandy mud across the area that's typically about a meter thick. And this is interpreted as primarily deposition from meltwater plumites that extends well out across the shelf. So these inner two cores are actually in inner Pine Island Bay. And a critical piece of evidence for the plumite interpretation is the strong peak of very fine-grained silt at 10 or 5 microns that shows up in the grain size analyses of this layer. We also know that there are really quite thick sediments in various local basins that show up in acoustic sub-bottom profiles operating at frequencies of several kilohertz. This example here is from our cruise, and the location is shown by the red star on the multibeam bathymetry map at the bottom there. The problem with these kind of data is they only penetrate really soft, fine-grained sediments, so they're not showing us the full picture. There's also a couple of short seismic reflection lines with air guns that have been collected near the front of Pine Island Glacier. This one is shown on the map. The extent of that one is shown by the magenta line there. And there's another one that crosses this at right angles, but this is very limited extent. And these data are not really ideal for looking at shallow sediments because they're quite low frequency with limited bandwidth, as you can probably get the impression from what you're seeing there. So what we need to investigate the true extent of sediments in inner Pine Island Bay is something with more penetration than a sub-bottom profiler, a 3.5 kilohertz sub-bottom profiler, and something with better bandwidth than those old seismic lines. So this is the equipment we took on the Palmer in 2020, a short solid streamer with a lot of short channels and a couple of generator injector guns. And this was our survey plan for a network of lines in front of Thwaites Glacier, which I've overlaid on a Sentinel-1 image from around the end of the season, and you can see that the ice really had no intention of letting us sort of carry out our pre-cruise plan. So in the true spirit of most Antarctic research cruises, we had to sort of reinvent this on the hoof. Yeah, and so this is the actual network of lines that we managed to acquire. Superimposed, obviously the ice moves around a bit, so look, we didn't really go through those icebergs. And this is what that survey plan looks like overlaid on the multi-beam bathymetry grid. So let's have a look at a few of these lines, starting with the line along the axis of Pine Island Bay going towards Pine Island Glacier. That's what this looks like. And the first thing you can see is that this shows that the relatively thick sediments near the front of Pine Island Bay Pine Island Glacier that were identified previously, this is quite an extensive, thick layer that continues more than 40 kilometers from the front of the glacier. And given that the glacier, we know, extended out to the shelf break at the last glacial, fast-flowing ice flowing through here for a long period of time, I really think it's very unlikely that such an extensive sediment layer survived the last glacial period. These, to me, I'm pretty certain these must have been deposited rapidly during the grounding zone retreat. So we can also look at now the crossing line that runs parallel to the front of the glacier, and there also you can see there's an apron of thick sediments. And in fact, this apron of sediments is on the seaward flank of the ridge that Jenkins and co. showed that the ice shelf was pinned on until the 1970s. So something else that, interestingly, that we see in the data is in several deep parts of Pine Island Bay, we see these local sediment mounds containing arched, fairly continuous reflectors that are quite unlike anything we'd expect to see in glacial or proximal glacier marine deposits. And I think what these are is small sediment drifts. And if I'm correct about these, then they potentially hold a record of the rate of circumpolar deep water inflow. Except now the problem is that sediments in this depth in Pine Island Bay are usually barren of microfossils, so they're difficult to date. But perhaps we can get some sort of chronology from using ramp pyrolysis or relative paleointensity dating, and we could get the current speeds out of something like sortable silt. So that's an interesting opportunity for the future. Here's another one. The first one on the left is where the red oval is on the map, and this one on the right is where that magenta oval is. So something I did mention at a WAIS meeting a couple of years ago is what we also see on a number of seafloor highs in Pine Island Bay. There's evidence of sediments on the flanks and over the top of them. So the first example at the top there, that line cuts across the edge of the high that the front of the eastern ice shelf, the Thwaites eastern ice shelf, is pinned on. So that is very certainly was a pinning point, and I think the lower one was probably a pinning point as well, and that's on the northern flank of Pine Island Bay. So I've highlighted here with this semi-transparent orange fill what I would regard as sediments. And I think the significance here is where we've got sediment over the tops of the things that were former pinning points. We have to think about the fact that this means that there wouldn't have been really high drag over these right up to the point that an ice shelf detached from them. So something I'd like to come back to now is what's the significance of this extensive thick sediment layer in front of Pine Island Glacier? So, I mean, something we know is that if a grounding zone stays in one place for any length of time, this usually results in construction of something called a grounding zone wedge. And on the top left here's an example of one that Phil Barton colleagues surveyed in the eastern Ross Sea. Quite large sediment bodies, they imply, and on the right there's a sketch of how these things are thought to form that I drew quite a few years ago based on something that Richard Alley had produced. So what this implies is that there's really quite a lot of sediment transport at the base of ice streams, either in a deforming till or maybe, as Luke has been explaining to us, more likely frozen into the base of the ice now. And so if this is the process we've got going on with a flux of sediments that I've denoted FS there, let's think about what that means depending on where the grounding zone is. If the grounding zone stays in one, if we divide our bed into a series of equal sized boxes, if the grounding zone stays in one place for a length of time, then all that flux is being delivered, in this case, to box one, and it's simply that sediment flux times the length of time is being delivered to that box. And because we see the way grounding zone wedges are constructed, it looks like most of that stays fairly local. If we have a retreat rate, R, then into each box you get the flux times time divided by 1 plus R. So essentially, the importance here is that the retreat rate dictates your thickness of deglacial sediments for a constant flux. So if you have a really fast retreat rate, that's when you get a continental shelf that's barren of deglacial sediments, so which is what we see over much of the inner shelf of the Amundsen Sea. So I would suggest that, because what this layer is telling us is that in the later part of the retreat, it was relatively slow and steady going into the inner part of Pine Island Bay. So I'm out of time, aren't I? Okay, I'll leave my conclusions up there for people to look at. Okay.
And we have Peter Neff up next, telling us about a U.S.-Korean collaboration. Thanks, Peter.
Awesome. Thanks, Thomas. Yeah, I'll give you more of an update on our plans for the coming field season with the new Korea-U.S. and growing other international collaboration, establishing an ice core array along the coast of West Antarctica to help us understand the critical processes and drivers there for what we're all talking about. And I wanted to just have an overview ice core slide here to sort of remind you why I try to always be here, and I guess that's sort of what I inherited from my supervisor, Eric Steig, who used to attend more frequently the WAIS Workshop, is that ice core records really allow us to explore processes, trends, and extremes in places and at times where we wouldn't otherwise have observations, because we don't have any research stations anywhere out along the coast of West Antarctica where we're seeing all of this change. And so through these records, through the geochemical proxies we're able to produce from the snow and ice, we can give perspective on climate, environmental change, glacier change, and ice sheet sensitivity in a warming world. These key questions, and adding especially that temporal perspective in just about anywhere along the coast of West Antarctica, so long as we can get there to collect an ice core record. And that is a large challenge. If you've been to the WAIS Workshop anytime in the last 8 years, you've probably heard me natter on about us needing to do this, collect ice cores along the coast of West Antarctica, and I think we have the opportunity this season to do that for the first time. So we're all familiar with the diverse processes and drivers and things interacting along the coast of WAIS, and I've sort of boxed up here in red where I think ice cores can most readily contribute. So, gaining better understanding of the global factors that impact WAIS or thwaites, however you want to generalize the systems that we're trying to understand, from changing winds to the teleconnections to the tropical Pacific, having long-term high-resolution records of climate, of temperature, of winds, of sea ice, polynya variability are really going to help us understand the impact of those global factors. Documenting snow accumulation, variability in time and in space. You can really only do that best with ice cores or shallow cores on the ground. And then understanding these persistent features like the Amundsen Sea low and its influence on the Thwaites Glacier and West Antarctic system. That's just sort of where ice cores come into this big complex problem that we're all contributing to better understand. We're really lucky in West Antarctica to have a pretty darn good spatially and temporally coherent ice core array through work in primarily the late 90s, early 2000s, with a little bit more work in the 2010s. So credit to that, and I always might come across as I come down hard that we don't have enough ice cores in West Antarctica, and having so many dots on the map might not be convincing there, but I hopefully can convince you that we need a little bit more information. So this is a bit of the highlight rap sheet of what we've learned from ITAS. So really important things. We documented that the warmth we saw in the 1990s in those records was rare but not unprecedented in the last 2,000 years. We actually really struggled to demonstrate the statistical significance of that because our records really end in the late 1990s and early 2000s, and we don't have that recent time documented. Work by folks like Dave Schneider, who's here, and Eric Steig suggested that a strong El Nino in the 1940s might have played a role in the initiation of some of the widespread retreat we're seeing in the Amundsen Sea region. That still goes back and forth whether or not that really seems like a key player in what's going on there. And then we're seeing continued struggles for climate models and paleo data to agree on the trends we see in temperature and snowfall and winds. So continuing to get more records and have more interface between the paleo community and the modeling community, I think, is a key goal going forward as well. I I saw this paper that came out just earlier this month, and it sort of highlights the fundamental challenge we have, maybe more on the atmospheric side of documenting change, emerging signals of climate change in Antarctica, where essentially we have one of the noisiest atmospheric systems on the planet, if not the noisiest, and we have short records in time, and they're sparsely spaced across the continent. And particularly in West Antarctica, we don't have a coastal bias in where our research stations are. We only have inland stations with long-term observations. So this is a stack of 78 ice core records over the last 1,000 years. And the chart on the bottom is sort of another problem we have in ice core science, is that we have a great number of ice core records coming up into the 20th century, and then we drop down to 0 records by the end of the 20th century. So we have no ability to in anywhere because we haven't back to visit the places where we collected so many great ice cores in the 1990s and the 2010s. So we have a sort of an obligation to keep our arrays of ice cores across Antarctica updated, which is an opportunity, because it's actually not that hard to update these ice cores. So that's sort of a separate point that I'll come back to. So we have these ice cores in West Antarctica, but we have a really big blind spot on the coast if we're thinking about all of these ice-ocean-atmosphere interactions. We're not sampling the low elevation regions where everything gets much more complex than this sort of high, dry, distilled interior where we have most of our ice core records. And we have, thankfully, these ice rises, essentially mini ice sheets that ring the Antarctic continent that are ideal from an ice core perspective for collecting ice cores and having an interpretable paleoclimate record. So I nicked this figure from the Developing Rings community paper that shows where we hope to go to this season. And I'll get a little bit more to that. Julia Andreasen, with support from NASA, has been doing really good work trying to learn as much as we can from the Operation Icebridge data we have, trying to pull out annual layers and variability in snowfall from those. But it's going to be really helpful to have ice cores on the ground to tie to, or at least an ice core on the ground to tie to. So that's what we're building towards this season. And I have been highlighting this opportunity for the last few years, and I would encourage, I guess I included sorry, I'm stumbling over myself here. I include this slide because this is essentially how I have now come to this opportunity of having a field opportunity to collect an ice core. I put out this idea in the journal Oceanography a couple of years ago, and it was a little bit scary to do that, so I think encouraging ECR folks, if you have ideas that you think others are going to be into, it's sometimes scary to put them out there because it feels like they might be grabbed away and not be your opportunity, but it also is an opportunity for you to get visibility and potentially people to come to you, and that's what's happened to me. So this is where we hope to go this season, and I'll just take you out there. Brooke Medley always reminds me that from the air, these ice rises look like nothing, but if you have the right camera, back in the 60s when you're mapping these places for the first time, this is Martin Peninsula where we're planning to go with the Korean icebreaker this season. And I share this just so you can sort of see, the Amundsen Sea there, some of the sediment cores that Rob just showed are literally there in the frame, and we can have an ice core right there up, elevated above the ice shelf in a place where we like for reconstructing climate near the Getz and Dotson ice shelf on either side of Martin Peninsula there. We have a long list of things we can learn. I'll breeze through that because I'm going a little bit long, but we have the fundamental high resolution, time resolution of ice cores, annual reconstructions of climate and environmental conditions through the chemical proxies we develop. You can get temporal variability and surface mass balance, look at new processes like atmospheric rivers, as Emma Robertson highlighted yesterday. And if we get radar data as well, we can start to learn about the long-term stability of these ice rises and potentially learn about the value of deeper drilling or collecting rock samples from the bed of these ice sites. Once we understand the quality of paleoclimate record we can reconstruct at these places. So the challenge has always been, how do we get there? We all know it's very hard to operate in the Thwaites region, and thankfully I've have this new partnership that's developed with the Korean Polar Research Institute to get out there on the RV Aeron this season, supported with helicopters to bring a full-size ice core drilling system to collect an ice core. So we hopefully will get out to Martin Peninsula come January, collect actually 2 cores, 250-meter cores is our goal. We have the U.S. ice drilling program 4.0 drill already on the way to get loaded on the ship, and it'll be myself and Julia Andreasen with 1 ice core driller on the U.S. side and a similar sized team on the Korean side with a drill of their own to try to drill 250-meter deep ice cores that would be sort of 200 to 400-year-long records of variability out there. We also have a radar team developing with support from Vikram Goel, Kenny Matsuoka, and TJ Young to bring snow radar, deep radar, and PRES out there for those important measurements, as we've heard over the last few days. So to not go long, I'll just say we're starting to chip away, I hope, at closing the gap here, and hopefully over the next few years we get additional opportunities. I know I'm probably the one person that's not listening to Kelly's advice to not try to base my tenure on field work, but so far I hope I'm going to not just be a bad example in a couple of years and tell you it was a bad idea. So we're excited to get out there. I think in addition to getting new ice cores, we need to make sure that we're keeping our current ice core arrays up to date. Again, the number of records we have plunges in the 2000s, so we need to fill that gap. We can do that with really simple, shallow drilling if we can get out to these sites sometime in the next 5 to 10 years. So thanks so much. Sorry for going long.
Cool, thanks, Peter. So continuing to highlight the friendship between radar and ice cores, Shivangini Singh is going to tell us about radiostratigraphy. Oop, sorry, that's your last slide, not your first slide. Try that again. Come on.
Hello everyone, I'm Shivangini Singh, and I'm a second-year graduate student at the University of Texas at Austin. And today I'm going to be talking about establishing a radiostratigraphic connection between the South Pole and Hercules Dome. So we've all heard a lot about radar sounding, and it's an important method to image and characterize the end glacial structure of the ice sheet in broad areas. And it's an important complement to ice core analysis since it can help us be informed of flow path and possible disruptions to the age stratigraphy at ice core sites. And what causes these bright reflections in radar data? Well, it can be contrasts in density, acidity, and believe it or not, even bubbles. So here's an overview of the most recent airborne geophysical survey conducted by Coldex this year. We conducted around 15 flights flying out from the pole to the southern flank of Dome A. And for the purpose of this presentation, we're going to focus in this area between the pole and Herc Dome. So here's what it looks like. Shout out to Jamin for designing the flight path for this survey. So I'm going to be focusing on the SPICE-7 flight path and the F-19 flight beneath that. So here's what I've been working on. On the left is the latest data acquired by UTIG's radar MARFA, and on the right is an old dated survey conducted in the Pole and Pensacola Basin, which was conducted around 1998 with a system that's a direct ancestor of the current radar that we use. And you can see the layers are quite, the layers are visible better in the latest data compared to the older data, which works out great for us. And we basically exploited the crossover design strategy of these surveys to propagate the chronology through the ice sheet. And here are some examples on the left of some tie points that we've used. So it started out great. I started tracing on the SPICE-7 transect, and we were able to obtain age-depth relationships for 9 isochrones going back to around 94,000 years. And I used a software called Landmark by Halliburton, which ironically is also used by oil and gas industry to map out the subsurface, but it works out great for us. So it started out great, but we hit a snag as we progressed towards Hercules Dome. So this is a topographic high that we've affectionately labeled Mount Doom. Since we could not circumvent around it and connect the ages from that side, but well, after that, I tried to connect it from the F-19 side, and we ran into Mount Mini Doom. So unfortunately, I wasn't able to go down to the older layers in the ice sheet column. And that's where, roughly around where they're placed. And yeah. But now since we know where Mount Doom and Mount Mini Doom lie in the subglacial topography, we hope to plan our flight paths in a way that we can circumvent these features in the coming field season. So far, we do have a continuous coverage for the 4,700-year isochrone, and we hope to use this to better ascertain accumulation rates for this region. We do have some coverage for the 51,000 year layer, though I will say that I'm not quite as certain beyond Mount Doom and Mount Mini Doom. Sorry, I mislabeled that. But yeah, there are definitely older layers in there, and hopefully the next field season we'll be able to map them out. This is what we're planning on doing for the next year, this coming field season. We hope to sort of miss these two subglacial highs, and we also hope to refly some of the transects we flew over Herc Dome to facilitate repeat pass interferometry, and hopefully we'll be able to derive some end glacial vertical velocities out of these. So with that, I leave you with this. Thank you.
Thank you. Next up, we have Yongji Wang telling us about machine learning for ice rheology. Oh, should be all set.
Yeah. Hi, thank you, everyone. So I'm Yongji Wang, so a postdoc at Princeton. Oh, sorry, at Stanford University. So today I would like to talk about. That's because I just changing my title. So today I will talk about discovering the complex flow law of ice shelf using the deep learning techniques. So as we know, the ice shelf is a flowing extension of grounded ice, which play a critical role in slowing ice discharge into the ocean. And in general, ice shelf can be considered as a two-dimensional flow, which is governed by the shuttle shelf approximation equation. But however, to predict the ice flow, there are remaining one unknown quantities in the equation, and that is the ice viscosity, and which need to be determined from the ice rheology. So ice is known as a non-Newtonian fluid. So for solid ice in the lab, so a simple relation to describe its rheology is basically is usually the Green's flow law, which has also been widely used in the ice sheet model for decades. But however, the rheology of glacial ice can be much more complicated and actually remain under debate. So therefore, measuring the actual rheologies of ice shelves becoming very critical. So leveraging the remote sensing data, so prior studies based on windy theories actually claim that so the power law exponent of the ice shelf rheology is actually close to 4 instead of 3. But however, such method can only be applied to some windy areas, which are very limited on the ice shelf. But however, for the 2D ice flows, examining the rheology becoming very complicated. This is because the effective stress becoming no longer can be determined explicitly. So to solve the problems, we recall that actually the viscosity is defined as a ratio of the stress with the strain rate. And with the strain rate can be learned from the velocity data. Then an alternative way to determine the effective stress is actually trying to infer the viscosity. And with the remote sensing data, we can find that viscosity becoming the only unknowns in the shallow shelf equations, which can actually be calculated by solving the equation, and usually known as the inverse problems. And to solve the inverse problems, so there are existing a lot of classical methods, such as control method. But however, here we would actually propose a new deep learning techniques, which is called the physics-informed neural network, or called PINs, to solve this type of problem. Viscosity network which represented the 4 variables involving in the shallow shelf equation. And then with the remote sensing data, we are able to train a neural network with output of the velocity and the thickness to match these data. And at the same time, we can substitute all 4 output into the governing equation and the necessary boundary conditions to infer the viscosity. And then by minimizing the residue of the equations as well as the difference with data, the problem becoming well posed, and we are supposed to able to get the viscosity. So to confirm the method work, so we create some synthetic data by solving the shallow shelf equations with a given viscosity profile. And then, now we are doing in the rectangular domains. And the color showing here representing the value of each quantities. And then by using these synthetic data, we are able to successfully infer the viscosity via pins, which actually match very well with the given profile as shown here. So then, confirming this method, we are allowed to using this pin method to analyze the real data of the ice shelves. And we also show a very high accuracy. And then, based on the definitions, we are now able to explicitly get the effective strain rate and the stress by their definitions. And then now we have the full information to trying to examine the full ice shelf rheology. And here's just a quick result, which showing the ice shelf rheology, also the stress and the strain relations on 2 random locations on ice shelf. Unfortunately, we see no clear, none of the regions give a clear relation, and also seem to follow different profiles. And this kind of implies that the rheology of the real ice shelf could be much more complicated than what we expect. So in order to learning the ice shelf rheology better, so we decided to check the stress and the strain relations along a single flow lines connecting from the upstream to the downstreams. And this allows us to knowing the stress and strain so this allows us to know the ice rheologies, to review the evolution of the ice rheologies as it travels through the entire ice shelf. And here is the result, which is based on 15 independent experimentals to confirm its robustness. And we can see that at the beginnings, along the flow lines, so the relations first initially follow a tilted straight lines, but gradually turns into a vertical line. The interesting question is that what actually determines this turning point? And with systematic analysis, we actually realize the turning point actually matching very well with the boundary between the compression zone and the extension zone of the ice shelf. So this means that if we only plotting data in the compression zone only, we see a very good power law relations. But however, if we plot the data in the extension zone, we see some perfect plastic rheology, which is the vertical line. And this also implies that maybe the so the classical power law rheology might no longer be valid to describing the rheology over there. But however, due to time limit in this talk, I will mainly focus about the result in the compression zones. So to confirm the result we find is accurate, we also detect and analyze the compression zone on different other ice shelves around Antarctica, which all show a very clear power law relations. And in addition, we are very excited to find that we also see that the power law exponent, in fact, also following a very clear patterns. So when the stress is less than 100 kPa, we see the exponent is actually close to 2. But however, when the stress gradually increases, we see the exponent start to increasing from 2 to 4. And this result naturally reminds us of the well-known experimental results from Goldsby on ice rheology, which also show the similar result that the power law exponent actually will be increased with the stress from the lab experimental. But however, to confirm they have some matchings, we have to do more systematical and quantitative comparisons. And to do that, so in a simple form, So what the result finding by GOES-B is also known the composite rheology. And in a simple form, the composite rheology can be mainly composed of two mechanisms, which we call the grain boundary slidings, or called GBS, or the dislocation creep. And with the coefficient determined from the data in GOES-B's paper directly, actually there's only one free parameter, which is the grain size in this entire form, which is hidden in the GBS terms. But since the dislocation term have no any free parameter, we can first compare it with our data. And we can see that for the ice shelf under low stress, so the contribution of the dislocation creep actually is almost negligible, as shown here. And this also implies that under low stress ice shelf, the rheology might also follow the GBS mechanism. And then by fitting with the GBS term with the data, we see a very good agreement as long as the inferred grain size is around 1 millimeters. And such GBS dominated mechanism rheology are also be found on other ice shelf under low stress, such as Larsen Sea ice shelf and the Nathan ice shelf. And also the inferred grain size on those ice shelves also will be around 1 millimeters. But compared to those ice shelves, so the compression zones in around the bird ice streams on the Ross ice shelves experience some slightly higher stress. And we can see in that cases, the dislocation creep start to taking effect at the high stress end, as shown here. And then by matching the entire composite rheology expression with data, we can clearly see that the power exponent at the high stress end is starting increasing from 2 to becoming 3. And finally, we're also finding a compression zone on the Nathan ice shelves, which further experience higher stress. And in that cases, with no surprise, we find that in that case, the entire data was captured by the dislocation creep by himself. But however, we recall that the dislocation creep does not involve in grain size. So this means that we are not able to determine the grain size on that locations directly from the expressions. But in general, under the higher stress areas, it is common to assuming that the grain size actually already reached a steady state. And then based on the semi-empirical relations available in the literature, we can directly finding that the grain size under the stress of that compression zones will also be around 1 millimeter. And very luckily that we also find that they do have a few measurements on those within these compression zones, which also show that the mean grain size is indeed around 1 millimeter, very well matching with the inference. So far we already showed that actually the ice rheology, so the ice shelf rheology in the compression zones kind of like a very well does follow in the composite rheology. But actually there's one remaining question we have to answer, is that why the inferred grain size on the ice shelves from our data under the low stress actually becoming much less than the supposed steady state grain size. And to answer this question, we consulted our collaborators, so the Professor David Pryor's, which actually give a very nice explanations. So the reason is actually simple, is because when the ice when the ice under stress on the ice sheet, as well as the flexure zones near the grounding lines, so the ice prefer to recrystallize and also will follow the steady state size. But however, after being discharged into the ice shelf, so the stress of the ice suddenly drop. But however, the time it takes for the ice grains to grow back into the last half shelves is actually take much more longer time than its traveling time in ice shelves. And this kind of like time limitations really leading to the ice shelf rheologies falling down into the grain boundary slidings mechanisms. And this kind of result can also be confirmed, partially supported by our measurement on the Nathan ice shelf, which involving two different compression zones and the different stress. But however, as you can see, the inferred grain size actually are very close to each other in these two compression zones. And here we just want to summarize that the reason why we think in ice rheology is important is really because either the grounding line flux as well as the grounding line position is really highly depending on the rheologies. So this means that the right quantification of the ice shelf rheologies will really help us to predicting wells the ice mass loss, and as well as in turn the sea level rise. And here the summary of my talk. So the bigger two take-home message is just that we're thinking that the ice shelf rheology is really different in the compression zone and the extension zones. And in the compression zones, by systematic analysis, we verify it's still following the composite rheology. But the interesting is that actually the extension zone actually covers 90% of the ice shelf. So therefore, in the future, understanding the real rheology in the ice shelf, in the extension zone of the ice shelf, will be also more important to understanding the entire fate of the ice shelf. Yeah.
Thank you. Cool. Could we, and if you can stay up here, if we get all our speakers to come down here. Oh, okay.
Test. Danny and I are gonna, or Thomas and I are gonna walk around. So just raise your hand if you have a question, and we'll bring you a mic.
Thanks. Good morning. Peter, I was kind of wondering about some of the ice rise work you're talking about. It's my understanding that if you're at these lower elevations, you're going to sacrifice a lot of resolution because of melting that might kind of blur out events. And so, for example, at the WDC site, there's a really nice sharp peak of elevated accumulation. And it doesn't show up at the Rice site on Roosevelt Island. So I don't know, I was just kind of curious about your thoughts about that.
Yeah, I mean, the time scales are much shorter for what I'm initially talking about at ice rises. You know, getting a couple 100-year-long records. I mean, the resolution is higher because the snow accumulation is higher down there. The melt layers are somewhat of a concern, but in that environment with the temperatures, you're going to be getting, depending on what elevation you're at, you're going to be getting melt that forms a pretty isolated lens. It's not going to be moving through the snow very much. And those can be a really great direct record of warming. Some of the most compelling records of climate change in Antarctica are ice core melt records from the Antarctic Peninsula. So, yeah, I mean, if one could get multiple ice cores, it would be nice to experiment with the sweet spot of like where in that elevation with respect to temperature is going to get the right balance of melt layers on the hottest days, but no washing through a stratigraphy.
Thanks. This question is for Marion. Nice talk. So are the requirements to apply the kind of analysis that you did a continuous sedimentary record, like no missing record in the stratigraphy, and your ability to date it? Are those the key components you use to apply it in other locations?
So there are missing parts of the record, especially as the glacial advance came in the last time. There are pieces missing from MIS 3 and MIS 4. But I think the key part is the geochronology, is to be able to pinpoint the time. And what was really useful is we also used optically stimulated luminescence, which I didn't talk about here, but that was a really key one, especially when looking at transgressive or regressive facies for those shoreline movements. And so I would say like being able to use geochronology would be one of the keys, but if there's missing time, I don't think that that's necessarily going to bar you from being able to see this in the record.
I guess my question is really to the last talk by Yongji. Yeah. So it's really interesting work, and of course, it's a really advantage with for a field where you have a lot of data, and so of course the implication to me is also very profound. And you show that basically the exponent n increases along the flow line from n equal to 1 to this highly non-Newtonian non-Newtonian exponent. And of course, that to me that implies that you really, as the stress increases down the stream line, and that's very easily you can get localization, rifting, and things like that. Now, my question to you is, of course, when you model the ice flow, as far as I can tell, you introduce a number of simplifications, such as shallow water approximation, and also I was also kind of curious about how you actually model the bedding. Of course, the sliding is very important. How you, I guess, a couple of experiments showed yesterday, right? And the sliding, the bedding, that seems to me also could really influence how you model the ice flow. So I was curious if you can actually comment on the kind of approximation you introduced in modeling ice flow, which is important for rheology, how that actually would impact your conclusions.
So thank you for your question. So first I want to clarify that I'm thinking for most of the results showing in this talk, they are basically on the ice shelf, which and also slightly away from the grounding line. So which actually we don't have any, so we can assuming that the free stress on the both top and bottom surface. So we're thinking the shallow shelf ice, so the shallow shelf approximation equation can really describing in general this very well. But your question is trying to next step. We also about the connection from the ice streams before the grounding lines to the ice shelf after the grounding lines. But just exactly as you said, just because we roughly don't know very well what would be the governing physics that, or how to, although, for example, Professor McKay also involving having some ice stream equation that is considered a sliding boundary, but in that case, they have one more unknown terms, which is the basal stress, which in our case is, if we only having the data, which is based on the surface velocity, actually to infer some more rheology on those areas will become, so the problem will become ill-posed. That's why we're also very looking forward to see whether there might be any people doing the field study or doing any radar analysis allowed to at least have some location, having some profile of the velocity along the z direction, which we already see there's some lot of studies people doing in the talk yesterday. So as long as we can gain enough data, which can confirm that the data required by our model in the ice stream or even in the ice sheet, in the middle of the sheet, is enough to make the problem well posed, then we very like to also analysis the rheologies on the ice sheet and also on the ice stream to see whether it will also have a big change from the middle of the ice sheet to the ice stream and finally go to the ice shelf. But right now, based on the data available to us, the last phase, which is ice shelf, is the only thing we can do. Yeah. Thank you very much.
Okay, yeah, we'll do next, yeah. Go ahead, Brett.
I have a question for everyone. Thank you all for a really awesome session. I think there's a lot of talk, and well, most of the talks are about field work and collecting data, and I'm wondering, typically we think of collecting data, we help, evaluate models, but often models can inform, where we want to sample, where we want to go, and I'm just wondering what your all perspective is on trying to, use models in an informative sense for when you go out and you do surveys and things like that.
Because I'm just a modeler, so
Sorry.
but I'm very willing to hear the answer from the other speaker.
In the region that I work in, I'm really interested in the interactions between tectonics, sea level, and glacial isostatic adjustment. And so I feel like glacial isostatic adjustment modeling is really useful, not only in the system I'm looking at, but also in Antarctica. And so that would be something I'd be interested in, the direction of where that's going.
There is a really nice community of modelers who have become involved in the Rings project to try and do exactly that, to design where are the places that we need to have better constraints and where is the uncertainty focused. So one of the things that I showed was that estimate of where the grounding line was going, so that we can work out, okay, where will we need to understand flux gates in the next 100 years? Where might that be? And then can we go upstream from there for the other basal constraints? And there have been similar efforts looking at how does a different interpolation of the topography affect the models that run over the top of it, and how does that all build into the uncertainty estimates? So that is happening and could always use more hands.
Yeah, that's a great question, Brooke. And I don't think you meant to tee yourself up, but I look at the sort of ice core informed models that you've put together of like surface mass balance variability across West Antarctica and some of the places where we see, westerly wind forced trends that are very strong, but they're in regions with some of the least ice core constraints. That's, informs where we might want to go. And then of course we rely very heavily on reanalyses, climate reanalyses of the atmosphere, which we rest a lot on without sort of acknowledging how much they're just not tied to observations as well. So that we can always inform that, but we use that to, at any of these ice rises to see what the climate controls on snowfall should be. So for a site like Martin Peninsula, where we're right next to Thwaites Glacier, our snowfall controls there are going to be pretty much the same as what controls snowfall that's arriving on Thwaites, like high pressure in the Bellingshausen Sea. And then sometimes, so we look around sort of from the potential ice core site perspective, we look at how we can get diverse signals in this controls on snowfall. So if we actually go further from the Amundsen Sea, we're getting more snowfall control from the westerly winds and things like that.
Well, in the context of the Coldex data, that's a pretty loaded question, because that's exactly what we're trying to find out, where we can find the oldest ice. But I guess for the Herc Dome, we just want to find a location where we can potentially have access to the last glacial maximum in the western Antarctic ice sheet. And that's exactly why we're trying to trace the stratigraphy. So yeah.
Yeah, thank you for that question. The one thing that ice sheet modelers always tell you they want more of is denser, better bed data. So that's partly what drove us to complete the detailed bathymetry coverage in Pine Island Bay and to find out about the nature of the bed there. So it's not the modern bed, but it's the bed that Thwaites Glacier has retreated from, and we've been able to show by comparing profiles that it's actually a very good analog, because bed data on the ice sheet itself is much more difficult to get extensive bed data anyhow. It's also, bathymetry data is incredibly important for, accurate bathymetry data for modeling the ocean flow on the shelf, so that's another motivation. And where we still don't know that really accurately is under the ice shelves, of course. So I think that's a priority for the future. I don't know if we can still do better with gravity inversions, but we can certainly do better with autonomous underwater vehicles if we devote some effort to that.
Hi. Hi, a quick question. So I think I'm wondering if there's an example of a modeling finding informing observations even in this panel. So Yongji, that was a fantastic talk. So you talked about grain size being super important. And you had the idea that the grain size gets reset as it goes over the grounding line, yet you might expect grain size to change, depth average grain size to change as you travel through the ice shelf, partly just because you have snowfall falling on the ice shelf. So my question is actually for other people, thinking about the radar, thinking about the ice cores, thinking about Kirsty's design of rings, what geophysics can tell us this distribution of grain size or depth average grain size or something to help out with this? Because clearly the modeling is saying grain size is super important, something we don't think about very much. How can the observationists respond to that? And I don't know if this is an out there question, is there geophysics that can tell you something about grain size? Thanks.
I can say something because, so basically if you know that, also starting from a modeler, just say, and then just like a fluid dynamics to people. So because as long as if we know the accumulation of the snow, and also and at least you can measure the velocity, then maybe somehow you are able to developing, for example, some solidification effect and also porous medius effect that able to quantify that how the snow ice at the top surface over the transition of the ice started becoming condensation and then becoming too firm and eventually to it. But I thinking So as long as I'm thinking as a modeler, if you have few data which have a borehole measurement around different area around the ice shelf, can confirm the model in a general way, then it will give us a lot of confidence to saying that our model could be correct. But I'm thinking we also track a lot of results for about grain size. But most of the grain size we find is basically on ice sheet, but not necessarily on the ice shelf. So the result I'm showing around the nascent ice shelf is something we only finding around the ice shelf. But if there's more like depth information on the ice shelf, then I think it can help us as a modeler to learn much more about. Because although the ice shelf can be, people always using depth averaged, but you never know whether there are some impurity or something which is depth dependence can significantly changing the property of ice shelf, which we actually maybe neglect in our classical assumption.
Yeah, Johnny, I'm just thinking sort of, there's like a disciplinary separation maybe in ice core science too of, what we would call physical property measurements in an ice core, like guilty as charged, we often view as quite separate from a paleoclimate reconstruction from the chemistry in an ice core. So, if it's valuable to have those measurements, in my case, from an ice rise near an ice shelf, we need to know that. And that's part of the reason we come to workshops like this and say, hey, we're going to do this and bring some ice back, and there might be the opportunity to do that. But then, if you want physical properties information on ice shelves, you're never going to find an ice core scientist who's going to drill a climate-focused ice core on an ice shelf because your deep layers are coming from a mile upstream, and that's not helpful for our reconstructions. But if you need to be going out there to get those measurements with ice core drills, we should make sure that that's captured, like in our community science planning documents, is that sort of thing.
I have a question for Peter. So when you're looking at accumulation variability and climate change in this part of Antarctica, a lot of that is funneled through patterns that we're seeing in changes to the Amundsen sea low and blocking highs over the Bellingshausen and the peninsula. So when I think about climate change in this area, I think about a couple different ways in which that's happening. One, maybe just in terms of warming, another in terms of how the Amundsen sea low itself is being impacted. So I'm wondering, when you are taking ice cores or want to take ice cores in this region and are thinking about how climate change is operating, what do you think the advantages are to looking at climate change through the lens of these multiple stages of atmospheric effects in this area, where you do need to disentangle some of what's happening locally versus globally, versus other areas of Antarctica that are less affected by these more persistent low and high systems and might be more susceptible to different scales of variability?
Yeah. It's climate is really complex in Antarctica, and the change that you see is really regionally variable. And our ice core reconstructions, like certainly a criticism of coastal ice cores from ice rises, is that they reconstruct a relatively limited region, on the order of extending in a hundreds of kilometer radius where that information is going to be relevant. So thankfully, your question sort of sets up an argument for multiple ice cores. Like, we know that the controls on snowfall at any ice core or any ice rise are totally different in the Amundsen Sea versus if you come around towards the Ross Sea. If your snowfall there, when you're out on the West Coast, not in the Ross embayment, like not at Roosevelt Island, you're out on the open South Pacific Ocean where you're getting a lot of marine moisture. A site out on that western edge of West Antarctica, the snowfall is almost entirely controlled by the westerly winds way out with no relation to the Bellingshausen Sea high pressure system. So you can isolate different components of that, but unfortunately you need multiple ice cores to do that. And that's part of the grand plan. But and this is why I'm so nervous about just resting our confidence on the atmospheric reanalyses that we have, or that our inland arrays are good enough. The systems that we are also concerned about are where the ice enters the ocean, and we currently only have information from hundreds of kilometers away from that. Yeah, so it is really complex, and I think it'll be really confusing if we only have one ice core from one location on the coast, and so we're going to keep trying, and I'm really hopeful that the mode of logistics of working with the Korean icebreaker and helicopters works out. We have, I mean, I didn't get into the specifics, but we have 21 days for science in the Amundsen Sea on this cruise, and potentially 10 days on the ice for ice coring. So we've got a big challenge, and thankfully with support from NSF and the ice drilling program, we have the resources to go really hard and be really ambitious and try to get a 150-meter deep ice core, and then we also are prepared to scale that back as we always have to be in polar logistics.
I have a question for Rob. Nice talk, Rob. I'm kind of curious about, I can see where you're going with the approach you were presenting there. You didn't talk about any of the dates, the rates of retreat. So any thoughts about where that's heading with you?
We have of dates from Inner Pine Island Bay, really. In terms of retreat, I mean, we know that the ice grounding zone had retreated into Inner Pine Island Bay by the early Holocene, and after that it's not very well constrained because it's a short distance, and I mean, there's a paper coming out shortly from in front of Thwaites which shows that, again, by the early Holocene, the grounding zone was even closer to where it is today in Thwaites. We've been waiting for this one to come out for a long time. Julia may be able to tell us. I don't know. We've got a publication date yet? Soon, yeah. It's been soon all year. Yeah. So, yeah, I mean, I can't give numbers on that at the moment, apart from we're looking at some time in the Holocene. But, yeah, I mean, the point I was making is how do you get a shelf that's barren of deglacial sediment when we know the ice streams are delivering so much? I think the only way you can do that is to have rapid retreat.
Yeah, I agree. And, it's kind of interesting that you brought that up, because I think, early days, back when you and I were young, we always kind of recognized that there's this tremendous backstepping that was occurring between wedges on the outer shelf. And I think we all kind of recognize even then that, wow, there must be some rapid shifts in the extent of grounded ice. But like you said, we've never had the age control. And I'm noticing, like in this particular area where there's just so much discharge, it's hard to get the good geophysical control that you're going to need to talk about the volumes. And then we have the added challenge of getting the chronology. So lots of challenges there.
Yeah, and I mean, a really big challenge is actually getting a good handle, when you have got a really fast retreat, getting a good handle on it, because you would need such precise dates, and even if you get a really precise date, it's still a minimum age. So, the actual retreat age for that point is sometime earlier, as you well know.
Yeah.
So, it seems almost intractable to me. We can never define the highest rates. We can only see that it is high. Yeah.
There is great value in those minimums, too. As well. But the other point I wanted to make is that the importance of getting a really good stratigraphic geomorphologic control, because we need to know the orientation of these features in 3D to kind of estimate, okay, well, is it a grounding line retreat at some unusual angle because of where we could collect data, or is it really representative of the center line rates, which would be the maximums?
Absolutely, Phil. What we need is 3D seismic data.
We need 3D seismic data. Thanks.
Is it my turn? Another question for Rob-ish. So Marion said, GIA is real. We need to be thinking about this. This definitely can be a stabilizing feedback. So it's not totally barren of sediments. You showed some perch drift deposits and pretty thick 100 meters of sediments. And Terry's been talking about, tilting of this entire basin quite rapidly. I mean, even since the unpinning in the 70s, we're talking about meters of change. Is there any evidence for post-deposition deformation in the sediment structures you're seeing or anything like that, where we can actually look at these pinning points and know whether how long they've been doing this GIA thing?
I mean, the evidence for the long-term GIA comes from study of raised beaches. There was a paper last year by Scott Braddock and co, which showed during the Holocene we've had something like 40 or 50 meters of uplift. I think his record only went about half of that, so 20 meters in 5,000 years, something like that. So that's the kind of long-term amount of uplift there's been in Pine Island Bay region. And yeah, I mean, that's something you've definitely got to consider when you're thinking about unpinning of pinning points, that the pinning points could likely have stayed in contact for longer. Yeah.
I just think the kind of regional scale GIA story over that length of time scale is quite different from the story we're seeing today, which is very complex. I mean, you go from 5 centimeters per year, kind of inner bay, towards Crossan, all the way out by Abbott, where you're subsiding. It would be.
Yeah, I mean, I think Terry will tell you that's kind of expected. That's the outer bulge collapsing, presumably. Yeah.
But you haven't seen any evidence of in the seismic data itself.
I don't know quite how you'd see that. Yeah. I mean, because we're dealing with things that are at several hundred meters water depth, so things going up and down by even 50 meters are not really obvious. I have to think about that.
All right, I think we can take one last question because we're almost out of time.
This question is for Marion. Awesome talk, thank you so much. I wondered if you could speculate or kind of zoom out on the meltwater pulse 1A question to say like what you think your findings can contribute to that, or just jump into the fray.
Definitely, thank you for that question. I think because there is uncertainty in where all of that water was coming from, because it's not all accounted for, having the timing pinned down of how long that southern lobe of the Cordilleran was around is really useful to say, this much ice hadn't already been contributed, so by 15,000 years ago, and it was still around by 12,000 years ago. And so I feel like I don't want to go on my Cordilleran rant because this is the Western Arctic Ice Sheet Conference, but I feel like the Cordilleran Ice Sheet is really misunderstood or like not well understood, and so my postdoc project is further looking into what it was doing around the last glacial maximum. Yeah, that's my meltwater pulse 1A thing. Didn't mean to derail, but.
Alrighty, awesome. Can we thank our speakers again for awesome talks?